All right, hey class. Y'all have your second trig identities quiz coming up, covering just the sum and difference identities. That's it, meaning lessons 6, 7, 8, 9, not 10. 10 is where we go into the double angle identities, and we have decided those are going to be split. We're going to make this quiz into two quizzes, so you just need to know about 6, 7, 8, 9. This video will probably only cover lesson 6, and I'll do one for 7, I'll do one for 8, I'll do one for 9, I'll do 4 different ones. So here goes. So here we go. The identity that we're talking about, the sum and difference identity. First of all, again, the packet's not perfect, but that's okay. Where it says sum and difference identity number 1, it should really just say sum identity. And then there's the difference identity. Because if we were going to write this thing out at all, then we would have one identity that was the sine, I don't know what I'm saying, cosine. But it'd be the cosine of the sum of two angles, alpha, beta. And then the other identity is for the cosine of a difference, alpha minus beta. But as you guys know, I actually like to just combine these into one identity. But just, for now, we'll write it out. Again, God, you guys should know this. If you're coming to this video, you should at least know what the identities are. But the identity for cosine is cosine of the first angle multiplied by cosine of the second angle. And then if it's a sum, if you're doing the sum of alpha plus beta, then it's actually a difference here. And then you do the sine of alpha times the sine of beta. And that's the identity. So the other identity is the exact same thing, just with the signs reversed. It's going to be the cosine of alpha minus beta becomes the cosine of alpha times cosine beta, and then it's plus sine alpha sine beta. All right, so why? Why would you ever care? In all honesty, of course, you'd probably never actually care. But here's one thing that it's useful for. You all remember our good friend the unit circle. Our good friend the unit circle gave us a way to use geometry to actually come up with the exact value of a handful of trigonometric expressions. So if you wanted to know the cosine of 0 or the cosine of 90, you could do it. If you want to know the cosine of 45, you got it. You want to know the cosine 30? You got it. And if you want to know the cosine of 60, it's right there for you. So I'm talking about these angles, right? These positions here. Well, I wonder if it ever bothered you. I wonder if you ever lay awake at night wishing that you could find an exact expression to model the cosine of 15 degrees. Doesn't it just look like it belongs there? Look at these angles, all 15 degrees apart from each other, and then this big initial jump of 30 degrees. Annoying, right? Well, now you can. Now if you wanted to, you could find the cosine of 15 if you wanted to. Or, more to the point, the actual question on the paper, cosine 75, that would be this angle here, the one that's right smack dab between 60 and 90. So suddenly we have actually all the 15-degree incremental angles of quadrant 1. We could find them all now. And the way you do it is, well, I just kind of got finished telling you that we already know the cosine of 30. Cosine of 30, that's here, is root 3 over 2. And we know the cosine of 60. 60 would be right here. Cosine would be 1/2. And so you might notice that cosine of 75 could be re-expressed as the cosine of 30 plus 45. And then according to our identity, the cosine of 30 plus 45 would just be cosine 30 times cosine 45 minus sine 30 and sine 45. And of course, if we knew all of these cosine values, we know all the sine values too. We know what sine of 30 is. It's 1/2. And we know what sine 45 is. It's root 2 over 2. And I'm realizing I forgot to put that one over here, but it's root 2 over 2. But so what we can do now is we can add to our list these sort of 15-degree reference angles and 75-degree reference angles, because we can always use a combination of 30s and 45s or 60s to re-express our 75s and our 15s as sums or differences, and then apply this identity. And basically we're turning an unknown trig expression into known trig expressions that we can use to find the actual answer. So that's enough huffing and puffing. I'm already writing behind my own face. So I'm going to do something so I don't do that anymore. Hold on. Okay. So there's sort of the background. There's the underlying idea behind why we would ever want to know this stuff. So now let's just actually do it. So I think I'm just going to make some room and we'll actually do the problem. We don't need any of that. And again, this is the one problem that everybody should already have in their notes anyway. So if you want to fast forward, be my guest. Oh, let that go away. There we go. Okay. So like I said, if you wanted to find the cosine of 75, you're going to break it down to a 30 and a 45, express it as a sum. Then our new identity kicks in. You're going to do cosine 30 times cosine 45. And since we're doing a sum, we'll do a difference now, and we'll do the sine of 30 times the sine of 45. So cosine 30 is root 3 over 2, and cosine 45 is root 2 over 2. This will be 1/2 root 2 over 2. So go ahead and multiply. Radical times a radical, you can just multiply the radicands. 3 times 2 is 6. When you're multiplying fractions, you do multiply the denominator, so this will go to 4. And this will be root 2 over 4. Alright, we are now subtracting fractions. And so no, you don't subtract the denominators. As long as they have the same denominator, you just keep that. And in the numerator, you don't subtract the radicands. These are considered unlike terms. A root 6 and a root 2 might as well be an x and a y. Okay, you can't combine them in any way. So you literally just give root 6 minus root 2. And that is your answer. And so you leave it alone. That's the answer. So there. And again, I know I did this in class, at least I think I did, but I can kind of show you the deal. Yeah. It's kind of annoying. Put it here. Alright, so on your calculator, basically what just happened is we just evaluated cosine 75, right? So cosine 75 is this ugly irrational number. It's this repeating decimal. And so what we just figured out is that the exact value of the cosine of 75 can be expressed as root 6 minus root 2 all over 4. And so now you can see that first decimal expansion that you see here for cosine 75 is equal exactly to our final answer down here. So that's the goal of what we're doing in these first couple lessons. Lesson 6 and lesson 7 are both about taking cosine expressions that we previously could not evaluate, and now we can evaluate them using our new identity. Okay, so we could try another. Well, I don't really know if we need to. I'm pretty sure I did 2 in class. 2 is actually a homework problem because it's even. So I guess I'll do it. I think that's what most of you guys come here for, is to see your homework and make sure you're doing it right. And it gives me a chance to talk about how to figure this out again. I don't know. Maybe I won't do it. Let's do a different one. Let's do 4 or something. There is no 4. Okay, so I guess you got to do these. Cosine pi over 12, that looks all well and good. Let's find a more interesting one. I don't know if there are interesting ones. I kind of explained this already, but there's only so many angles I could ever ask you about, right? Where'd my little unit circle guy go? All right. I was going to go find a unit circle, but I don't really care. Again, you guys can imagine, you can picture that on the unit circle we only had these 3 positions that we could do, the 30, the 45, and the 60. And I explained that we now can do 15-degree reference angles and 75-degree reference angles. Well, that only adds 8 new positions to the unit circle. That's 15-degree reference angles in all 4 quadrants, so that's 4. And then 75-degree reference angles in all 4 quadrants, that's 4 more. So there's literally only 8 questions I could ask you, really. Okay, cosine of, this thing is one of those positions. Now, again, there's infinitely many because we could rotate all the way around and then stop here, but who cares? That's not a different question. There's only so many angles that we can really use. So I'm not going to keep hunting for like a quote-unquote good one. They're all good. And more to the point, what you also know by now is a fair bit more about symmetry. So even if we knew what 11 pi over 12 was, I'd like to think you know by now what 11 pi over 12 is. Again, 180 is pi, so if we treat pi as 12 over 12, then you're just 1 pi over 12 away from there. So you're talking about a 15-degree reference angle that's in quadrant 2. So that's going to be the same thing as 1 pi over 12 in quadrant 1. Now it's cosine, so it'll actually be the opposite of the cosine of pi over 12. This is something I expect you guys could do by now, is basically just say that I'm not going to evaluate cosine at this angle that's outside of quadrant 1 when I can just use the reference angle from quadrant 1 and make it negative if I need to. You don't even always need to, because guess what? If I'd given you this angle here, which would be what? Well, this is 2 pi, so you could treat it as 24 pi over 12. So let's pretend I'd asked you for 23 pi over 12. You would know that that's the same as the cosine of pi over 12. And in this case, it's not even the opposite of it. It's literally the same because they're both positive, because they both fall to the right of the y-axis. So this is something we should be able to do, is always rewrite it. And I mention this because all we got to do is go back and, well, that's number 2. So if you had already done number 2 and come up with some final answer, then for this one, the answer you're going to get is just the opposite of the answer that you got from number 2. And if I had asked you for the cosine of 23 pi over 12, it's literally going to be the same as what you got for number 2. So when I tell you there's only 8 possible angles, it's not even that. There's really like 2, right? I guess 4. But there's only 4 possible answers. There's this answer, and there's this answer, which is just the opposite of that. And then there's the value from up here. Anyway, I think I'm flapping my lips too much, so I'm going to just do another problem. But hopefully if you guys weren't understanding this, you're understanding it better. I don't know. So it's at least interesting to know that we could do this problem as the opposite of the cosine of pi over 12. But I'm not gonna. Let's just attack it more directly. So what 2 angles can you come up with that add up to 11 pi over 12? Well, I told you that one way to think about breaking this down is to just literally think about it as pi's over 12 and think about how many you need. And one way to do this is just to say that, to get 11, I could certainly do 1 and 10, or I could do 2 and 9, or I could do 3 and 8, or I could do 4 and 7, or I could do 5 and 6, or I could do 6 and 5. Wait a minute, that's the same, right? 6 and 5 is the same as 5 and 6. So at this point, you're not adding new options anymore. And then what I told you to do from here is, remember, these are actually pi's over 12. And so you'd want to reduce these. This is actually a pi over 6. These are both divisible by 3, so it's 3 pi over 4. And it's at this point, I hope, that you realize that this would be a great way of doing this problem, because pi over 6 and 3 pi over 4 are both unit circle angles. Pi over 6 is a 30-degree reference angle, so we would be able to evaluate there. And 3 pi over 4 is a 45-degree reference angle. It's just over in quadrant 2, but would be able to evaluate there. So that would be great. Notice the first one though is very bad. 1 pi over 12 we can't evaluate. That's a 15-degree reference angle that we don't actually have the value of memorized. Now we could find it, but too much work. So what about the 3 and the 8? That actually works too, because 3 pi over 12 would reduce down to pi over 4, which is evaluatable because it's 45. These are both divisible by 4. You get 2 pi over 3. That's evaluatable. That's just a 60-degree reference angle from quadrant 2. So that's a different one that will work for us. But then notice the 4 over 7 is bad because 7 pi over 12 is bad. That doesn't reduce at all, so it stays a pi over 12 that we can't evaluate. And same deal for 5s. 5 pi over 12 I can't evaluate because it's a pi over 12. We need to be working only with pi's over 4, pi's over 3, pi's over 6s, pi's over 2s. Those are the clean unit circle angles that we can evaluate. So anyway, there it is. There's your explanation again about how to kind of break these things down and figure out what angles to use. You could go with the lavender pairing or the green. Both will work. Both will give the same answer. You could do it either way. Let's go with lavender. So pi over 6 and 3 pi over 4. Alright, so again, now that this is all set up, you just use the identity which says that we'll be doing the cosine of pi over 6 times the cosine of 3 pi over 4. It's a sum, so now it's a difference, and it's now sine pi over 6 sine 3 pi over 4. And then just start evaluating. Cosine pi over 6 is root 3 over 2. Cosine 3 pi over 4, it's an x-coordinate, so it's negative root 2 over 2. Maybe throw this in parentheses. Since it's negative, you don't want to mistake it for like subtraction. So putting parentheses on it reminds you that what we're doing here is really multiplying. Alright, we're subtracting. Sine of pi over 6 is 1/2. And the sine of 3 pi over 4 is root 2 over 2. Now this one's still positive because we're in quadrant 2. And in quadrant 2, the y values are still positive. Oh, I did that backwards. But that's why the cosine is negative, but the sine is still positive, because we know in this quadrant we've got negative x's, meaning negative cosines, but we've got positive y's, meaning positive sines. So anyway, the rest should be a piece of cake. This is going to be negative root 6 over 4 minus root 2 over 4, which, how do we express this best? I think probably we factor out the negative, and we call it the opposite of root 6 plus root 2 all over 4. Which, if you were paying attention, you already heard me say it was exactly that, right? So if we had done the math on cosine of pi over 12, we would have found it to be root 6 plus root 2 all over 4. And then lo and behold, the cosine of 11 pi over 12 is the opposite of that, just like we thought it would be. So that's cool. Erase. Okay, so 4 is actually even. You guys can do that one yourself. I will just say that if you wanted to find two numbers that added up to this, just know that if it ends in 5, you definitely have to use 45. So probably the easiest thing in the world to do is just use the 45 and whatever 55 minus 45 is. So 210. That's obviously a pairing that's going to work, right? And then 45 is what? Quadrant 1. And 210 is a 30-degree reference angle. That's down here in quadrant 3. But both of those angles for sure are evaluatable. So you could expand this out. You could do it. You'll be done in a minute. So what's 255? 255, if you think about it, is an angle that rotates and pulls up 15 degrees shy of 270. So this is a 75-degree reference angle from quadrant 3, which means if you really wanted to, you could rewrite this as the cosine of its reference angle, 75. But of course, cosine 255 wants to be negative, since it lives in quadrant 3. So if I'm evaluating cosine at a quadrant 1 angle, you know the result's going to be positive. So you do need a negative on this. So instead of doing cosine 255, you could just do cosine 75 and make it negative in the end. This is a valid strategy. If you're more inclined to just attack the problem sort of directly and as written, you could be doing 210 and 45. What else could you do? You need a 45-degree reference angle. So the next 45-degree reference angle is 135. So if you're inclined, you could do cosine of 135 plus whatever gets you up to 255. So it's looking like 120. That adds up correctly. And then what you're working with now is two angles that are both from quadrant 2. The 120 being a 60-degree reference angle, the 135 being a 45-degree reference angle. I don't love this because then both the cosine of this and the cosine of that are both negative. Who cares? The two signs will be positive. You could muscle this out. Again, I just want to send the message that the way you break this angle down is absolutely not unique, right? Somebody could be doing 210 and 45. Somebody else could be doing 135 and 120. There's literally infinitely many ways you could break this down, because don't forget, we could even be doing the cosine of somebody minus somebody, right? For example, 45 again. Just add 45 to this. What do you get? 300 on the nose. Okay, you could do it that way. You could do it as a difference and just do 300 minus the 45. 300 is evaluatable. It's a 60-degree reference angle living in quadrant 4. So again, not unique. Think of any combination of values that are unit circle values and you'll get the right answer. Okay. I'll do the odds. I mean, I'll continue to do the evens. This one I'll actually do. So for this one, you can break it down, you can attack it directly, or you can say that 19 pi over 12, again remember this is 24 pi over 12, a full rotation is. So 19 pi over 12 has us pulling up 5 pi over 12 units short. So that's this position. If we had sort of our three evaluatable angles, here's 45, 60, 30. So 19 pi over 12, we're definitely talking about this guy right here. The one that's 5 pi over 12 as a reference angle. So we could turn this into the cosine of 5 pi over 12. And you can tell by the drawing that that does have the exact same value of cosine. Again, because if cosine is the x-coordinate, then the cosine of 5 pi over 12 from quadrant 1 is positive, but the cosine of 19 pi over 12 from quadrant 4 is also positive because they're both to the right where x's are positive. So I don't even need to modify this. So again, you are well within your rights to just kind of rewrite this and say these expressions are equal, so I'm going to evaluate this green one and I'll still be getting the right answer for the original expression. Again, I'm not gonna. I'm going to attack it more directly and just find two angles that add up to 19 pi over 12. So cosine, I don't like the size of this pen. Who's going to give us 19? With an angle that's kind of big, like 19 pi over 12, it just makes sense to do it as a sum. Keep both of the angles kind of small. I don't know, same kind of frame of reference here, same thinking as I still need a 45 degree, meaning I still need some kind of pi over 4. So we would get pi over 4 if we had 3 pi over 12. So 3 pi over 12 might just be kind of a standard inclusion here. And then if you take 3 away from the 19, we obviously still need 16 pi's over 12 to make up the difference. 16 and 12 both divisible by 4. So this is actually the cosine of 4 pi over 3, which is evaluatable. And of course the 3 pi over 12 is 1 pi over 4. So broken down this way, you've got a quadrant 1 angle, which should be very easy to evaluate. And then 4 pi over 3 is a quadrant 3 angle. So you know that both the cosine and sine of this are gonna be negative. So anyway, let's expand, let's evaluate. It's going to be cosine 4 pi over 3 times cosine pi over 4. Again, if we're doing it as a sum, then this needs, the expansion should be a difference. That's it. So now that we're expanded, we just have to evaluate that guy, evaluate this guy, evaluate this guy, evaluate this guy. And again, two of these are really easy. The cosine of pi over 4 is root 2 over 2. And the sine is root 2 over 2. And I'm not even worrying about the signs about plus or minus, because we know pi over 4 was quadrant 1. Everybody's positive in quadrant 1. Then, for the 4 pi over 3, again, that's quadrant 3, so everybody's negative. Cosine's negative, sine's negative. And what is the actual value? Well, 4 pi over 3 means we went 3 pi over 3, and then an extra pi over 3. Pi over 3 is 60 degrees, so you're talking about this position. And so cosine would be the smaller number, meaning 1/2. So it would be negative 1/2. And sine is the y value, so the longer number. So this one's the root 3 over 2. And so from here it looks like I'm getting negative root 2 over 4. And then minus a negative, so plus root 6 over 4. And then what I would do is I would switch these. If you've got a negative root 2 plus 6, just express that as root 6 minus root 2 all over 4. And that's going to be the final answer for 6. Okay. So hopefully you are understanding this well. 8. So all the evens this time are radians, and that's okay. I don't have much to say about this. We'll do 8. One thing I do want to say here is 24 pi's, that's a full rotation plus more. So anytime you've got an angle like this that's really, really big, then you definitely want to map it back onto a coterminal angle. 25 pi over 12 would mean we've come all the way around and then gone 1 extra pi over 12. Because again, 2 pi is 24 pi over 12. So that means this angle has come all the way around 360 and then a little bit more. So that drawing's not good. That's okay. So we know that we're basically just going to be able to do the cosine of pi over 12. And we know that those two angles would be exactly the same. Okay? It's basically like, if you can picture the graph of cosine, pi over 12 is like some angle that's really, really early on the curve. Well, 25 pi over 12 would be exactly 1 period later. So if you're kind of with me on this, the angle that you are given is the one right here that's just a little bit to the right of a max. So of course it's okay to say that you're going to get the exact same answer if you just evaluate at pi over 12, because that is in literally the same position, meaning just a little bit to the right of a max. And so that's what I mean by this. I hope this visualization helps it make a little more sense if it didn't make sense before. But if I just go, actually in this case I'm mapping backwards by a full period, and I'm just saying, hey, let me evaluate here at 1 pi over 12 rather than evaluating here at 25 pi over 12. It's just easier, right? So again, when your quiz rolls around, by all means, please feel free to just say that, hey, I'm not actually going to use the 25 pi over 12. I'm just going to evaluate the cosine of 1 pi over 12 because I know that they must be congruent because of, it's called periodicity. That of course any trig function is going to be equal at two different angles that are multiples of a period apart, because they're literally the same position on the graph, they're blah blah blah. Alright, now again, I'm saying that you can do that, but for the people out there who did this, you know, the other way by actually breaking it down, I'll break it down. So what would we do? Is anybody even watching anymore? I hope this is so easy that you're not even watching. All right, so what two angles add up to 25? I don't know. Pi over 12. And another pi over 12. As I said, we pretty much always need to be using a 45-degree reference angle, meaning we pretty much always need to be including a pi over 4, which means we pretty much always need somebody divisible by 3 up here. So we could just do 3 and 22, and that'll be fine. We could do that. But somebody else who's divisible by 3 would be, well, I wouldn't do 6. Why wouldn't I do 6? I wouldn't do 6 because 6 reduces down to pi over 2, and that of course is here. It's this position. It's not a 45. If you do 6 pi over 12, that's not going to be a 45, that's going to be a 90, and we don't tend to use the 90s and the 180s as we're breaking these angles down. We want to stick to the 45s, the 30s and 60s. So okay, don't do 6 then. But after 6 comes 9. 9 pi over 12 would be fine, because that would reduce down to, you divide by 3, and you'd have 3 pi over 4. So that's still a 45-degree reference angle. It's just a 45-degree reference angle from quadrant 2. Okay. Again, I don't want to overthink this, and I don't want to make a mountain out of a molehill. Just, oh, I do not know what I just did. What did I delete? The whole thing? The whole thing. Undo? Okay, we're back. All right. I think if you're keeping this as simple as you can, but still leaving it as 25 pi over 12, then just do the 3 pi over 12 to get your 1 pi over 4 and the 22. That seems the most obvious thing. So that means reducing this. I'm actually evaluating 11 pi over 6, which is fine. That's on the unit circle. And 1 pi over 4. So again, cosine, cosine, sine, sine. Cosine of 11 pi over 6 times cosine of pi over 4, sine of 11 pi over 6, sine of pi over 4. And again, if it's a sum, then this needs to be a difference. So where's this 11 pi over 6? Well, 11 pi over 6 would be 1 pi over 6 short of a full rotation, because a full rotation is 12 pi over 6. So 11 pi over 6 is just 1 pi over 6 away from that, meaning it's a 30-degree reference angle for us that lives in quadrant 4.